In the previous subsection, we examined the effect of a harmonic perturbation on a system initially prepared in a single state. We found that the perturbation can induce two kinds of resonant transitions. First, if the final state energy is approximately equal to h bar omega naught above the initial state energy, then the system undergoes an upward transition, which in the optical context corresponds to stimulated absorption or simply absorption of energy from the driving field. Second, if the final state energy is approximately equal to h bar omega naught below the initial state energy, then the system undergoes a downward transition, which corresponds to stimulated emission. So in that discussion, the focus was on transitions between the initial state and a single discrete final state. We derived the corresponding first-order transition amplitudes and probabilities, and we saw that the occupation probability becomes appreciable only when the perturbation matrix element is non-zero and the resonance condition is satisfied. Now, although that single state picture is extremely useful for understanding the physics of resonance, many real systems are not that simple. In practice, the final state is often not one isolated energy level. Instead, there may be a whole group of nearby final states or even a quasi-continuum or continuum of accessible states clustered around the resonant energy. And that changes the problem in an important way. If there is only one discrete final state, we ask for the probability of occupying that one state. But if there is a dense set of final states, then the more relevant question becomes, what is the total transition probability into all of the available final states near resonance? That is the motivation for this subsection. To answer that question, we must go beyond the probability for one specific final state and introduce the density of final states. This allows us to count how many states are available within a small interval of transition frequency or transition energy. Once that density is introduced, the sum over individual final states can be replaced by an integral over a dense spectrum. This is a crucial step because it is precisely what allows the resonant sinc squared factor to be converted in the long time limit into a much simpler and more universal form. Up to now, we have considered the transition probability into one specific final state f. But in many real problems, the final states form not just a single isolated level, but a cluster or even a quasi-continuum of states near resonance. That's the situation considered on this slide. Suppose the transition is an excitation process, so the final states lie above the initial state and are clustered around the resonant frequency, as shown in this figure. To describe the dense set or a quasi-continuum of final states centered at a given transition frequency, we introduced the density of final states per unit transition frequency, omega fi, and denoted by rho of omega fi. So rho of omega fi times d omega fi gives the number of final states within a differential interval, d omega fi, centered at some transition frequency, omega fi. A schematic plot of the density of final states versus the transition frequency is shown on the right. As seen in the figure, for the same small or differential interval d omega fi, if rho of omega fi is small at some transition frequency, then that interval contains fewer final states. On the other hand, if rho of omega fi is large at another transition frequency, then the same interval width contains more final states. A few important facts about the density of final states are worth mentioning here. In reality, the density of final states depends on the chosen initial state and on the electronic band structure. For a fixed initial state I, rho of omega fi times d omega fi represents the number of accessible final states whose transition frequencies lie within a small interval, d omega fi. Since the electronic energies vary throughout the first Brillouin zone, different initial Bloch states generally have different possible final states and different transition energies. Therefore, if a particular state is chosen as the initial state in a transition process, it can have its own density of accessible final states as a function of omega fi. A precise equation for the density of final states would be the one shown here, expressed in terms of the delta function. So the more explicit notation is rho sub I of omega fi, because the transition frequency depends on the chosen initial state I. Finally, it is further rewritten as rho of omega fi for simplicity. So in the case of excitation transition, the probability of transition from the initial state I into states lying within a differential interval d omega fi is given by the single state probability times the number of available states in that interval. So we write the expression shown here. Again, rho of omega fi times d omega fi gives the number of final states within a differential frequency interval d omega fi centered at some transition frequency. Also, the unit of each term is explicitly shown here to remind you that the transition probability is indeed dimensionless. Now summing over all such final states then becomes an integral as shown in this equation. This is the key transition from discrete state framework to continuum framework. Now we consider the constant matrix element approximation. That means we assume that the perturbation matrix element does not vary significantly over the narrow frequency range that contributes appreciably to the integral. So near resonance, we approximate the absolute square of the perturbation matrix element as a constant and pull it out of the integral. This is a very standard step in the derivation of Fermi's golden rule. Physically, it means that across the narrow resonant band, the coupling strength is approximately the same for all relevant final states. Again, the figure shown on the left nicely illustrates the idea of a cluster of final states near the resonant energy. The initial state is discrete, but the final states are densely packed, and the perturbation can drive transitions into that whole group rather than into just one isolated level. So this slide is where the derivation begins to move from single state transition probability toward a transition rate into a continuum of final states. Now we analyze the key integral that appears in the transition probability from a single state to a quasi-continuum of final states. The central function is the sinc-like or sinc-squared function. This function has several very important properties. As the time variable t increases, first, the central lobe becomes narrower, with first the zeros at plus minus 2 pi over t away from the center frequency omega naught. Second, the peak height grows according to t squared divided by 4, which can be easily obtained by taking the limit of this function as time t approaches infinity. Third, the total area is pi t divided by 2, which is independent of the time variable t. So as time increases, its central peak becomes narrower and taller. The peak is centered at omega fi equals omega naught, and the frequency span from the center frequency to the first zero, which is 2 pi over t, shrinks as time becomes larger. So for sufficiently long times, the density of final states, rho of omega Fi, changes only slowly over the narrow width of the resonant peak, as shown in this figure. This allows us to approximate rho of omega Fi as a constant and pull it out of the integral, as shown. Then the only non-trivial part that remains is the definite integral. Using the identity, we obtain this result. So this is the crucial long-time approximation. The deep physical meaning is that the sinc-squared resonance function behaves more and more like a delta function selector as time grows. It isolates the final states whose Bohr frequency matches the driving frequency, omega naught. So in the long time limit, the perturbation no longer merely produces an oscillatory amplitude. It effectively picks out the resonant final states and yields a probability that grows linearly with time. That linear growth with time is the signature that we're about to obtain a transition rate. So this slide is therefore one of the most important conceptual steps in the whole derivation. It shows how the finite time resonance profile becomes sharply concentrated around the resonant condition and converts the probability integral into something proportional to the interaction time t. Now we substitute the long time result back into the total transition probability. From the previous slide, we know that the resonance function, which is sinc-squared, behaves like a delta function in the long time limit, and its integral with respect to omega Fi is equal to pi t over 2. So the summed upward transition probability becomes this equation. Simplifying, we obtain the equation as shown. This is already an extremely important result. The total transition probability into the resonant group of final states is proportional to time. And once a probability grows linearly with time, the coefficient of t can be interpreted as a transition rate. Later, we will define the transition rate as the time derivative of the transition probability, resulting in Fermi's golden rule in the form where the density of final states is expressed per unit transition frequency, which can then be converted into the more common form using density of final states per unit energy.